Layer 2, or your data link layer. And if I were you guys, I would get in the habit of moving away from calling layers by their name and moving towards calling them by their number, because when you do go apply for a job, a person interviewing you can tell how experienced you are by whether you use the name or the number. So if you say layer 2, more experienced people just say layer 2. If you continually say data link layer, the person interviewing you will garner that you're not that experienced, that you passed your CCNA a few days ago. Anyways, moving on. The data link layer controls communication on the immediate link between two devices, or the immediate, as the name says, the immediate data link. So layer 2, once again, controls communication between one device and the next immediately connected device. So if I were to draw a pictorial representation of it, and I'm going to draw a circle in this class, every time I draw a circle, it means I'm drawing a router. And let's say this router is connected to another router. And whenever you see a thunderbolt being drawn in the Cisco world, it means this is a serial connection. Your serial connections on a router are your wide area links. So we're going to say this port on this router is serial 0/0/0. And I'm going to go into the naming conventions for routers in a little bit. It doesn't pertain to this part of the lecture, so rest assured I will be covering how Cisco names their ports, and there is a convention to it. And let's say the other one also is serial 0/0/0. This immediate link between these two devices, this immediate connection between these two devices is your local data link. So layer 2, your data link layer, controls communications on the immediate link between two devices. Now, we understand that the data link layer controls communication on the immediate link, immediate physical link, which I will change the rules in a little bit. But for now, the immediate physical link between two devices. Now, data at layer 1, if you were to think about the structure of data at layer 1, and if I ask you a question, what does the data at layer 1 look like? Your answer should be that the data at layer 1 is simply electricity, electrical signals, or changes in voltage. Now, at layer 2, the data has been put into a set structure. So at every layer past the physical layer, the data is put into a set structure. And this set structure is called your PDU, or your protocol data unit. At layer 2, the protocol data unit is called a frame. Now, what does a frame look like? Well, before we get to what a frame looks like, when there is data transmission between two devices, just like when there is data transmission between your home and somebody you're mailing a letter to, you need two pieces of information. You need your own house address, which would be your source address, and you need a destination address, which would be the address of the person you're sending the letter to. In a similar manner, at layer 2, you need an addressing scheme. The most common addressing scheme that we see at layer 2, and there are others, but they coincide with a later part of the class, and I will bring them up when pertinent. But the data stream at layer 2 needs a source address from which the stream is sent from, and a destination address which the stream is sent to. And the most common of these addresses is your media access control address, or your MAC address. Now, what does a MAC address look like? A MAC address is 48 bits in length, and it's written in hexadecimal. Now, I'm not going to assume that people here listening to this lecture know what hexadecimal numbers are. So, real quick, what are hexadecimal numbers, or in short, what are hex numbers? Hex numbers range between 1 and 9, and then A through F. So, hex numbers go 1 through 9, then A through F. So if I wanted to say 10 in hexadecimal, I would just say A. If I wanted to say 11 in hexadecimal, I would just say B. I hope I got my hex numbers across to you guys. Now I can get to what a MAC address looks like. Remember, MAC address is 48 bits in length and is written in hexadecimal. So an example of a MAC address would be 002A, A, B, C, D, 1, 2, 3, 4. Now, how does this number or this MAC address equate to 48 bits? Each one of these hex characters is 4 bits. So the 0 is actually representing 4 bits. The A is actually representing 4 bits. Now, as I said, A actually means 10 in hexadecimal. So if I were to expand A out into its 4 constituents bits, sorry for the mispronunciation, let's do that. 4 bits, okay, so we draw out 4 lines representing 4 bits. And each one of these bits has a specific value attached to it, and this value never changes. From the very right-hand side, you start with a number 1, then you double it, you get 2, you double it, you get 4, you double it, and you get the number 8. How do I get A out of these 4 bits? A actually stands for 10, right? So the 8-bit is on, and the 2-bit is on. The 4 and the 1 bits are turned off. That gives you A. Now, I'm going to erase this part because I need to explain other stuff about the MAC address. The first 24 bits in a MAC address, the first 24 bits, so where does the line, or do I draw the line for the 24 bits? This is 16 bits, 17, 18, 19, 20, 21, 22, 23, 24. So right at the B. The first 24 bits of a MAC address are your OUI field, or the organizationally unique identifier. The OUI field is designated by a governing body, and it cannot be changed. And this is vendor specific. So each vendor, for example, Cisco, Microsoft, Dell, each one of these vendors are assigned several OUIs, and these OUIs cannot be changed. The last 24 bits of a MAC address, the vendor can do whatever they want with them. So the first MAC address created by Cisco ever was probably a vendor-specific OUI field, and then 000001, and they went from there. 0002, so the 10th router they made was probably 00008, and so on and so forth. The 7th bit of a MAC address, the 7th most significant bit, and whenever I use the language most significant, I mean all the way to my left, over here, or all the way to your right. In the second 4 bits. So the 7th most significant bit, which would reside in here, because 4 bits here, then 5, 6, and 7th bit, which would reside in here, is called the UL bit, or the universal local bit. If that bit is turned off, which it is over here, if that bit is turned off, it means that this MAC address is universally unique. There won't be another MAC address like this, in theory, because even then, sometimes you run across MAC addresses that are the same, but it doesn't happen often. But in theory, if this bit is turned off, the 7th most significant bit is turned off, it means that this MAC address, quite possibly, or should be, universally unique. If for any reason this bit is turned on, for example, sometimes you have the option of changing the MAC address on a Cisco device. You have the option of actually typing in a MAC address. Then, if it is locally assigned, if that MAC address has been tampered with, so to say, the 7th most significant bit would have to be turned on. So when the bit is on, it means this address has been assigned locally. So let's go ahead and turn that bit on and see what happens. The 7th bit would reside in here. So again, 1, 2, 4, 8. Remember, at this end, you have 4 bits that denote this 0. So 4 bits for this 0. The 5th bit, 6th bit, 7th bit. So this bit, well, I won't write it because I have no space, but this bit, the 2-value bit, is your 7th bit. If you turn this on, and by default it was off, then you get 0, 2, 2, A, and then A, B, C, D, and 1, 2, 3, 4. So, if the 7th most significant bit is off, it means the address is unique. If it's on, that means it has been assigned locally.